protected, so.
Okay. Yeah.
Sorry. I can just do it too. So we go along. Other things, rational. What kind of properties does it have that make it distinctive from the other functions mathematically?
Does it have a horizontal and a vertical?
Has a horizontal and a vertical asymptote. So if you're going to use a rational function, we'll actually see one. For instance, if you look at pressure versus volume, as you push harder and harder and harder in on as you make the volume smaller and smaller, compress something more and more, what happens to the pressure? Keeps going up higher and higher and higher, and theoretically at least it would shoot off to infinity as you get closer to 0, so you have a vertical asymptote. On the other hand, if we were to take just the air in this room, seal it, and then just start expanding the room, what would happen to the pressure?
It would approach 0.
Decrease, and it would approach 0, so it has a horizontal asymptote. And so from looking at the physics of pressure-volume relationships, we'd say, oh, looks like it would naturally be a rational function. It's got both a vertical asymptote and a horizontal asymptote. Whereas logs have a vertical but not a horizontal, exponential has a horizontal but not a vertical. When do you see horizontal asymptotes in real life? Okay, so you have some sort of floor that you can't get below, and you have some sort of process that does what? Gets close to that value.
A carrying capacity of a population. It'll always just fluctuate around the maximum.
In fact, we'll be looking at those, the elk population, the bison population in Yellowstone. And yeah, there's a maximum population. You couldn't just, completely carpet the park and elk. Wouldn't work, they would all die. And so there's this upper limit to how high it can go. And so we end up with a horizontal asymptote showing up there. All right, and then what's distinctive about a square root? Right?
Doesn't it only appear in one quadrant?
It has a, we can actually move it around so that we can actually put it into multiple quadrants, but it has a starting point. So it doesn't exist for a while, and then somewhere it just kicks in and starts up. What about asymptotes? Square root having asymptotes.
Horizontal.
That's good.
Not horizontal.
Let's just kind of play around with it. You got the square root of x. If you plug numbers in, are you ever going to level out anywhere? If you plug bigger numbers in, you get bigger numbers out, and eventually it would go off to infinity. So, no asymptotes. But that's the idea. We do our experiment, we gather our data, we plot it so that we can try and see patterns in it. We look for that pattern, and then we have a bunch of named patterns that you've picked up over your history in mathematics. And what we want to do is take those patterns that we know, apply them to the data that we've got, and find the one that gives us the best information that matches it as closely as we can get it.
So we spent like 2 whole years probably in our schooling up to this point studying almost exclusively polynomials, right? Algebra 1 and 2.
Right.
Are they just not very useful for most like regression purposes?
I wouldn't say that.
But they're less useful.
No, well, when you get down, if you can find an overall general pattern, that's wonderful. We really shoot for that. That's great. And in that case, they tend not to be polynomial patterns. Linear and quadratic will show up in the real world, but not much else. Cubics do show up in some spots. But 4th degree polynomials and higher really don't show up in the real world as overall patterns for some phenomenon. What happens really, once you hit cubics, you're just about done with real applications of polynomials. Now there's a lot of theoretical applications of polynomials that are very, very useful. But in terms of directly going out in the real world and applying it, once you get to cubics, you have what are known as cubic splines. Once you've got a cubic spline, you basically got everything that's useful in the real world. And what we do with cubic splines is we say, I don't care what the overall pattern is. That's not necessarily what I'm interested in. What I'm interested in are small scale patterns. And so you go in and you take 3 or 4 points and you fit a cubic function to them, and it turns out the cubic functions have just the right pliability, bendability, that they can bend and fit pretty much anything very closely, very nicely. And they call those cubic splines. So once you get the cubics,
We do apply in physics though, like motion, velocity, acceleration,
jerk.
impulse, whatever.
Let's see, jerk is the third derivative. And once you hit jerk here, the rate of change of the jerk doesn't have a name. So yeah, they get there. But we do use them in some other ways. Second semester calculus, when you took it, you did Taylor polynomials. We're talking about infinite ones. Those have amazing applications, lots of different areas. But it's all pretty much theoretical. In fact, engineering classes you're likely to hear, okay, so we have a polynomial, we have the Taylor expansion. And it's like, well, let's just cut off everything but the first term. First term's good enough. And we just go use the first term, maybe the first 2 terms if we're really desperate. And then we forget about everything else. All right, time for a break. And in this break, we're actually going to move rooms. So you get to get up and walk. We're going to go down to room 261. So go ahead and pick up and we'll head down there.